Some more examples for a binomial distribution. A burglar alarm system has 6 fail-safe components. The probability of each failing is 0.05. Find the probability that exactly 3 will fail. So here, this notion of success and failure when used in a binomial distribution really means success is what we are desiring, what we want to happen, and failure is what we don't want to happen. Finding this probability that exactly 3 will fail, a success is a failure of the component. So let's use this to set up our binomial experiment. We have 6 fail-safe components, so n is 6. Probability of each failing is 0.05, so we're going to let p be 0.05. Probability that exactly 3 will fail, x is 3. And we can plug this into our technology. We could use the formula by hand, but the technology is a little faster, and that's okay. Binom.dist, x, n, p, and false, because we want exactly 3, and we'll type these in. Binom.dist, 3, exactly 3 will fail out of 6 total. 0.05 is my probability, and we'll type in false, and we get 0.002. That's a really small probability, and that's good. That's what we want when we're talking about components failing. We don't want components failing. So the probability 3 will fail is 0.002. If we look at the probability that none will fail, we'll set up the same problem, but this time none means x is 0. So back over in Excel, I'm going to cheat a tiny bit. I copied my formula over and everything stays the same except my x value turns to 0. So I'll go ahead and change that. And check it out. The probability that none of these fail-safe components will fail is 0.735. That's a really good probability. For our last example, we'll look at a historical case. Some of you who may have had biology classes, you may know this story. When Gregor Mendel conducted his famous genetics experiments with peas, one example of offspring consisted of 580 peas, and Mendel theorized that 25% of them would be yellow. If Mendel's theory is correct, find the mean and the standard deviation for the numbers of yellow peas in such groups of 580 offspring peas. So we're going to look at this first part of our problem, find the mean and the standard deviation for the numbers of yellow peas if we had 580 offspring peas. Now notice, this is a really big N, 580. Our calculator may not be able to handle it. So we will rely on some technology, Google and Excel, to calculate these numbers for us, if we were finding probabilities of specific values. Here we're not. We're just asked to find the mean, the standard deviation. But let's first verify that it is a binomial experiment. 4 qualities for a binomial experiment. We have success or failure, yellow or not yellow. We have a fixed number of trials, n is 580. They are independent. What happens for one p doesn't matter for the other p's. And then in step 4, the probability remains the same. Gregor Mendel did a lot of work with genetics. So he was taking purely green pea plants that gave off purely green peas, and plants that gave off purely yellow peas. And he was trying to determine what would happen if he crossbred them, if he mixed the pollen from one pea into the flower of the other. What kinds of peas would that new plant produce? Would it be green or would it be yellow? And so after a lot of experimenting, he determined that about 25% of the time we would have yellow peas, and the other 75% of the time our flowers would have green peas. Ultimately leading to this idea of dominant genes versus recessive genes. That green was the dominant gene for these peas and yellow was the recessive. So we do have a binomial experiment, and we can find the mean, n times p. Not too bad on our calculators. we get 145. And these are 145 yellow peas. We're asked to find the standard deviation, so I'm not even going to calculate the variance at first. It's inside my calculation for the standard deviation. So we'll do n times p is 145 times q, which is 0.75. Remember, p and q add to be 1. 108.75. And then take the square root, we get 10.4 for our standard deviation. Okay, so find the mean and the standard deviation for the numbers of yellow peas in such groups. The actual result, when he did this crossbreeding of the 580 peas, the actual result consisted of 152 yellow peas. Let's calculate the z-score for 152. Z-score is given by value minus the mean divided by the standard deviation. So we'll calculate that here. Value is 152 minus 145 equals, we have 7. 7 divided by 10.4, 0.673. This is very much less than 3. So I'm within 1 standard deviation away from the mean. His value was really close. The z-score verifies the closeness of his theorized value of 145. So he thought, because there's 25% that should be yellow, he thought he should get on average 145 yellow peas. Instead, he got 152 yellow peas. But that means he wasn't that far off. He was really close to his actual theorized value, suggesting that his theory is a pretty good one. When we're calculating binomial probabilities, it's perfectly fine to use technology to help us out. These numbers can get really big. The combination part of the numbers can get large if our n is large, and the technology handles the numbers pretty nicely. You are welcome to do some by hand. Just know that if we were to try to find probabilities for this specific example, with n being 580, we would likely get an overflow error in our calculator because the numbers are too big, if we were trying to do it by hand. So we can use means and standard deviations in the binomial probability distributions, similarly to what we were doing before with positions, and determining whether values are likely or unlikely to happen, more than 3 standard deviations away from the mean, meaning it's unlikely to happen. We can also consider probabilities that are less than 0.05. Even though we haven't touched much on this, an unusual probability is a small value, usually 0.05 or less. But this value could be something different. We could say that 10% or less is unusual, or 1% or less is unusual. So this idea of unusual could change, and it will change for us actually when we go into chapter 8. We'll be determining which of these values we deem unusual. But for purposes in this chapter and in chapter 6, when we talk about unusual probabilities, we're going to focus on 0.05 or less. 5% or less would be considered unusual, 1 out of 20. So keep that in mind. We could, for example, in our Mendel experiment, if we wanted to know the probability that we had 200 yellow peas, exactly 200 yellow peas, N was 580, P was 0.25, and we'll do false. Let's see what Excel gives us. 200, 580, 0.25, and false. And we get something really small, 8.274 e to the negative 8. Let's write down this, 8274. 82747. So that would be 8275 e negative 08. And for a reminder, this is scientific notation. That means times 10 to that power So negative 0.08 would be 10 to the negative 8 power. So we have 8.275 times 10 to the negative 8. Okay, 8.275. 10 to the minus 8 means we're going to make it smaller. I'm going to move my decimal place 8 places. 1, 2, 3, 4, 5, 6, 7, 8. I'm running out of room. And then I'll put in all these zeros with a 0 in the front because I like leading digits. Writing it a little bit neater. 1, 2, 3, 4, 5, 6, 7. And then 7 zeros and then an 8. That's our probability for exactly 200 yellow seeds, yellow peas. That's extremely unlikely to happen, less than or equal to 0.05. If we wanted to do something like at most 200, the only thing that would change in our calculation would be false to true. At most means less than or equal to 200. And notice here, if we just make that one change from exactly 200 to at most 200, it makes sense that this probability would be very high. Our mean is 145, so the probability of all the values from 0 up to 200, this should be a large probability if our average is 145. So we're being asked what's the probability for 200 or less yellow peas. If our average is 145, this should be really high. And it is 0.9999863. That's a very high probability, almost certain because it's so close to 1. So that wraps up our binomial distributions. We've done some examples with at most, like this one. We did some of at least earlier. We did some where we were adding different values up, like 2 or 4 questions, correct? We looked at finding the mean, the variance, and the standard deviation of a binomial distribution, and using those values to determine if we had unusual values. And that will wrap up Chapter 5.